Welcome back to our APES flipped classroom. We're continuing with talking about land and water use, and today we are talking about the combination of the two. So we're talking about irrigation. And this might be something as small scale as watering a garden, or it might be on the huge scale that we see here, where we have these irrigated circles in the middle of what is clearly a desert. So, as we mentioned in class, there are four main types of irrigation. We're going to start down here in the bottom left corner, and we're going to talk about flood irrigation. So with flood irrigation, the entire field is flooded. This is really easy for fields that have flood irrigation. Very often they have sort of little dikes built around the edge that hold the water in, or the field itself may just be a little bit lower than the surrounding area. So this is very easy, it's very inexpensive, but it can be very disruptive to plants because it can waterlog the soil, which effectively drowns the plants by preventing them from accessing air and oxygen through their root system. It is only about 80% efficient. It depends on the source that you look at. 20% of the water is lost to runoff or evaporation. Some will say that it's about 25%. The least efficient form is furrow irrigation. And with furrow irrigation, then trenches are dug alongside the crops and filled with water. This is also relatively inexpensive. The water seeps into the soil slowly, but it does provide a little bit more access to oxygen for the roots than flood irrigation. However, it is the least efficient form. About 33 to 40% of the water is lost to runoff and evaporation. We're going to drop down here and talk about spray irrigation. This is what we see most in the area around us. And spray irrigation is where there are spray nozzles, usually on a rotating set of wheels. So very often these are circular fields, and that water is pumped into those nozzles and it sprays out onto the field, much like a sprinkler. It's much more efficient than flood or furrow, depending on the system. Somewhere between 15 and 25% of the water is lost, but it is more expensive than either flood or furrow because it requires energy for the pumps, it requires energy to move the sprinklers, and then it's just simply a little bit more expensive in initial outlay as well. And then our last form is what we call drip irrigation. And drip irrigation is the most efficient form of irrigation. It's over 95% efficient. That means only about 5% of the water is lost. And almost all of that is lost to evaporation, not to runoff. However, this is the most costly form. It avoids waterlogging, it conserves water. It usually works as a system where you have either little plastic tubes or hoses that have small holes pierced through them, and those holes allow the water to slowly drip out. So very little is lost to evaporation, very little is lost to runoff. Unfortunately, in addition to being the most costly initial outlay, it also requires farmers to pick it up if they want to change the layout of the field or if they are tilling with heavy equipment. So it has to be removed and then replaced. Okay, so some of the issues with irrigation are waterlogging. And this is when soil is overwatered and it saturates the soil, and that saturation, that water fills all the soil pores. And so air can't get into those pores, which means that it can't get to the roots, which means the roots cannot take in the oxygen that the plant needs. This can stunt growth. This can lead to what's called root rot, which will eventually kill the crops. So what are the solutions? Well, using a more efficient form of irrigation, like a drip irrigation, Or more commonly, soil aeration, which is where either holes or cores are poked in the soil to allow air to enter and water to drain. So we have a couple of different ways of doing soil aeration. One is simply poking holes in the ground with some sort of a sharp tool. In this case, it looks like a pitchfork. Or what is called core aeration, where little hollow tubes are pressed into the ground and little plugs of soil are pulled out. And that creates this space that air and water can enter into that encourages deeper roots and new root growth. So this is why some of you may have seen your parents aerate their lawns, but it's also used commonly in agriculture as well. Okay, another issue with irrigation is soil salinization. And salinization means turning salty, right? So salinization is the process of salt building up in a soil over time. And it's important that we recognize that salt in this sense is the chemical definition of salt, meaning any ionic compound, not necessarily NaCl or sodium chloride. Whether we're using surface water or groundwater for irrigation, it's naturally going to contain small amounts of salt. And those amounts of salt are not significant, but when you have repeated irrigation of the same field over time, as the water evaporates, the salt gets left behind in the soil. So over time, the amount of salt is steadily increasing, and it can eventually reach toxic levels. It dehydrates the plant roots, it prevents growth, it can prevent the germination of new seeds. So how do we solve this problem? Well, using drip irrigation where you're not adding as much water, aerating your soil, flushing with fresh water, or switching to a fresher water source. So the most common way that farmers treat fields that have reached a toxic level of salinity is to flood them and then pull that water out and the salt will usually dissolve in the water and you remove the water and it will improve the salinity of the soil. All right, so how do we use water? Three main categories for human water use. The first one we're going to talk about is industrial. The number one user of waters for industrial category is power plants. Also, metal and plastic and paper manufacturing use large amounts of water. But you notice that overall, industrial is less than 20% of our water use. Then we have municipal. So this is the water for showers, baths, drinking waters, toilets. This is household use. So municipal meaning city. So this is simply household use of water. And then by far the largest category, 70% of human water use is used for agriculture, whether that is water for livestock or irrigation water for crops. 70% of the water that we humans use is used for agriculture. So where's the water come from? So we have aquifers, and we're going to talk about how groundwater interacts with aquifers. So groundwater in general just means water that is stored in the pore space of either permeable rock or sediment layers. Aquifers are when we have large deposits of groundwater that are usable by humans. We have two different kinds of aquifers. We have confined aquifers and unconfined aquifers. Both are replenished by groundwater recharge. So that's when rainwater percolates down through the soil into the aquifer. When we have massive amounts of impermeable surfaces like we do in cities, then that prevents the rainwater from percolating down through the soil. So that's a significant human impact with aquifers and groundwater. Unconfined aquifers, and here's an example of an unconfined aquifer, recharge quickly because they have any water that comes through the soil is going to enter that unconfined aquifer. Confined aquifers, on the other hand, tend to be longer term water deposits. They tend to recharge more slowly because they only recharge through certain openings. Because a confined aquifer is confined by an impermeable layer of rock. And so it can only recharge through the permeable areas. Now, we have a couple of different kinds of wells that we'll go ahead and talk about while we're looking at this image. So an artesian well, you might have heard that term, is one that taps into a confined aquifer that is under pressure. And when you have a confined aquifer that's under pressure, when you send a well down into it, then the water will push up the well in an attempt to relieve the pressure. And so these are like mountain springs that you see continually flowing, or some areas will have artesian wells, and those are continually flowing. More common is a well that's in an unconfined aquifer, and wells that are in unconfined aquifers, and some confined aquifers as well, require a pump and electricity in order to pump the water up from the aquifer. Only if the confined aquifer is under pressure does it flow. One of the consequences of our agriculture is that aquifers are depleted. And so an aquifer is depleted when we use too much of the water from the aquifer. And we have a couple of impacts of the depletion of aquifers. One is what is called a cone of depression, and that's where one user of the aquifer uses a lot of water. And that will pull the water in the aquifer, the water level in the aquifer, down at the area where that well is drawing. And when that happens, it may well take the water table, the level of water in the aquifer, below where the other wells are reaching. And so that can result in drying up of wells because the water table is too low for those wells to reach. And very often you'll see people have to drill another well, and it's deeper, which is of course more expensive and has more significant environmental impacts. Another big impact of the depletion of aquifers, and this is a problem in our area, is that the aquifer is very much like a sponge. And when the sponge is squeezed out and dried out, then it will absorb more water. When the sponge is wet, it really can't absorb any more water because all of its pore spaces are full. So when we have an aquifer near a saltwater body of water, so like an ocean or a bay, if the aquifer is full, then the pressure of the water within the aquifer keeps the seawater out. But when the aquifer is over depleted, then the water from the ocean can enter the aquifer because the pressure of the fresh water is not holding it out. If an area is relying on that groundwater as their water source, you've now contaminated the water source with salt water. And yet a third problem with the depletion of aquifers is subsidence. And that's where if you have an aquifer underneath the ground in an area and the aquifer is overused, the aquifer is depleted, then that can actually result in subsidence, in settling of the ground. So your FRQ for this is to describe how soil salinization occurs, and then to propose a solution to prevent or remediate soil salinization. And I want you to identify one disadvantage of the solution you propose. And that's it for today. As always, if you have any questions, please let me know. Look forward to seeing you in class.